Thanks, Jiyin. Welcome, everyone. Thanks a lot for your interest in today's webinar. Today, we're going to have Jiyin Zhang. He's currently a PhD student at the University of Idaho, Department of Computer Science. I'm actually his PhD advisor. Jiyin has been a ESIP Community Student Fellow for the recent year, working with the Semantic Tech Committee. His research is in AI, natural language processing, knowledge graphs, and also their applications for geoscience. And today he will give us a talk named Large Language Model-Driven Workflow Management in Geoscience, from proprietary to open models. So today is like this. Jiyin will have about 30 to 40 minutes for the talk, and then we have enough time for questions, comments. And after that, I think we just need about 10 minutes to discuss some committee business. At that time, people in the audience, if you're not interested in the committee business, like we're going to talk about proposals and other ongoing activities. If you are only interested in the talk, you can leave in before the start of the last 10 minutes. Okay, and for now, I will give the floor to Jiyin. You can start your talk. Probably you can do the screen share and start.
Okay, thank you, Marshall. Let me try the screen sharing.
Yeah, I can see your screen now.
Okay, great. So you are you looking at my slides or my desktop?
Yes, it's up.
I mean, okay. So let me start. So
yeah.
Hello everyone. Thank you for your interest. Today I'm going to introduce my recent work about the large language model-driven workflow management in geoscience, and I will mainly focus on the applications in the Minted API, and I will introduce the details later. So for the background, I think maybe everyone is already very familiar with the ChatGPT's launch, and maybe we are already incorporated in our everyday life. But I would like to emphasize that simply using the large language model like a ChatGPT as a chatting bot is not a perfect match in the scope of the data analysis. And in this work, we want to propose that we can further take the advantage of the large language models capability of understanding unstructured data and the adaptiveness in the complex workflow. And here are some challenges this work is about to address. So sometimes people just use the large language model without sufficient context knowledge. Therefore, the large language model might generate wrong content or restrained by the insufficient context. And sometimes simply using the large language model as a question answering system is not enough. We further propose to empower the large language model with the capability of calling data API, and we further apply the large language model in a complex multi-step workflow. And finally, we will briefly discuss the scalability for the proposed work. So in the beginning, I want to introduce the terminology of the RAG, the retrieval augmented generation. As I mentioned, if a user is talking to a large language model like a ChatGPT directly without a further context explanation, the large language model will only be able to answer the question by its own trained data. And sometimes nowadays many large language models is capable of search the website and answer the questions accordingly, but the search engine is sometimes not that reliable. And if we can have a more domain-specific knowledge base, it would be, and for large language model to look up to, like a library, then the generated responses can be more reliable. Here is a simple application using this random paper called the oxygen dynamic scales in the scope of geosciences. We just use this manuscript. Well, essentially, this paper is applied in our workflow as in the format of a PDF, and we managed to embed the PDF in the vector database and generate these two questions to the large language model of ChatGPT-4. So as you can see, if we simply paste these two questions to the ChatGPT-4 in our Chrome, say browser, you will not end up with a correct answer because this is very domain or the paper specific. So we managed to construct a workflow which is applying the large language model in the workflow of RAG, retrieval augmented generation. And as you can see, in addition to the question query, we also provide the similarity search to that paper. Therefore, the large language model can answer the question not only with the user request, but also with the similar context to that question from the paper. So it can answer the question perfectly somehow. Well, and using the commercial model or proprietary model from OpenAI, sometimes it's not always satisfying to the users because we propose that using the open models can increase the data privacy and security. Say, if you do have a paper, you want to make it as a knowledge base, but it's not published yet, running a open large language model on your local device will be your perfect choice. And in addition, you can also enjoy the customization and flexibility of the open model. Say you can easily to fine-tune an open model and run it everywhere. And also because the running of the open model is somehow can be described as a cost-free, because the only thing you need to pay is the device and the electricity, and you can easily to integrate it and control it in other workflows. And also, since this entire workflow is transparent and under control, you can easy to enhance the trust and reliability. So in our experiment setting, we managed to apply three other open models, three other popular open models, one called Mistral, one Gamma. Mistral is from the company also called Mistral. Gamma is from Google, and Llama 2 is from the Meta. The setting is as follows. We managed to apply the aforementioned RAG experiment, but this time we just separate them, the models into 4 groups. One from GPT-4, the other three are from the open model, and this is a screenshot showing how our open models works. You can see the PDF is also provided as a context, but we did not simply provide the entire PDF because somehow too long manuscript will escalate the hallucination or the errors for the large language model. So this screenshot is showing that it's also applied the similarity search to find the similar context to the question and answer it accordingly. Well, and grading the performance of large language models is also always a tricky thing. So one of the popular evaluation methods is just apply the human expert to manually read the generated results. And this time we managed to apply another GPT-4, which has no idea which answer is generated by which model. And you can just grade the large language model generated answers accordingly. You can see I just told it to provide a grade out of 10, and then provide two advantages or two good parts of the generated answer and two criticisms. And this is the example generated responses from Mistral by GPT-4. And in the end, you can see in the two questions, the GPT-4 matches gained the highest score in the question 1, which is a 9 out of 10. And in the question 2, the Mistral, the open model, which is only have the size of the model maybe 1 out of 10 compared with the GPT-4, beat the performance of GPT-4 in the question 2. So somehow we can see that the open models can match the performance to the the commercial models to a certain extent if we are providing the sufficient context. And well, in light of this, we will carry out the following works. So followed by the RAG experiments. This time we just managed to apply the large language models not simply as a question answering machine, but to equip them the capability of calling the data API. This is a open Minted Python package developed by our team and supported by NSF. This workflow is a package which is providing a machine-readable API for users to obtain a mineral dataset from Minted. Minted, which is one of the most popular mineral website and database in the world. Most of the datasets in that website are from the crowdsourcing and strictly monitored and checked by a group of experts to ensure that the mineral dataset to that database are reliable. And you can see we will need to install it and have a API key and to program the valid question to program the valid coding and to obtain the JSON files of the dataset. And well, I'd like to say this process is just requires some technical background to gain the access to the dataset from Minted. So we want to mitigate this technical requirement by constructing this workflow. You can see here's the result. So when the user just come up with a human natural language request, say, show me the pyrite records from Minted, and here are the pyrite species from Minted. You can see the constructed workflow can access to the Minted dataset directly and provide comprehensive results in the end. And here's what happened to in the backend. In the beginning, the user is posting the natural language request to the ChatGPT, and the GPT-4 can read the needs and code the tool accordingly. And the tool is which requires the programmed data query dictionary to carry out the query. And this step is also being covered by the ChatGPT because it's very powerful in the scope of programming. So it can easily to translate this natural language request to a machine readable queries and finally conduct the query and answer the question accordingly. Answer the request accordingly. And this is just a very simple application. Here is a more complex workflow. You can see also built based on the open AI large language model, which is ChatGPT-4. We managed to apply this workflow. Say the user is works as a starting point to this system. When users have some certain request according to the mineral or geosciences, somehow the supervisor, the supervisor here in the flowchart is the role of the to manage the entire workflow, and was supported by a open AI large language model. It can read the request and decompose the initial request into several subtext, including the geomaterial collecting, locality record collecting, network plotting, and heat map plotting. And this entire workflow is fully driven by the supervisor, and the only thing the user needs to do is just to come up with the request, and the entire data analysis workflow from dataset preparation to the subsequent processing and visualization are executed in sequence automatically. You can see here is the details behind that workflow. In the beginning, the user can come up with a complex request, say plot the network of element distribution of iron minerals, and the supervisor will decide to decompose the task into two parts. One is calling the collector to gain the dataset, and second is pass the downloaded dataset to the plotter. And the action nodes, as I mentioned, are formed by the Minted API and the visualization tools. And after carrying out the request, the supervisor will read the outcomes of the action nodes, say, and determine that, okay, so now the user request is perfectly fulfilled. I can return the result to the user, so you will come up with a result and end the entire workflow. And sometimes if the action nodes are just failed, maybe there something happened within the workflow, the supervisor will call the action nodes again. So it's just calling a large language model in a for loop until it is fulfilled. So just to mitigate the low quality responses generated by the system. And here is an example, given the user input of plot the histogram of that mineral elements. So the entire the histogram can be plotted in seconds without further Minted API manipulation or the visualization programming. And here's what happened in the detail in the backend. This time the example is more complex compared with the formal example. You can see in the beginning the supervisor is parsing the human request and decided that it should call the collector to do the collecting, and the collector is do the similar things like our first example of min-dat searching. And after the collector obtain the requested dataset, you will return it to the supervisor, and supervisor will call with the dataset in hand, you will pass the dataset to the plotter and do the plotting thing. So as you can see, this part, the green icons represent to the agent tools, which is highly customizable. You can call different data API and apply different data analysis methods like machine learning, deep learning, and different visualization tools, and to expand the scope of this workflow. And here is another example. You can see the user can come up with a very relatively complex request. Say he wants the network of the mineral distribution, must have some element, must not include some element, and in very specific crystal systems. And the workflow can also translate or convert this human request to the min-dat API querying directionary perfectly, and call the network visualization tool to fulfill the user request. And here's another example. You can see the users want the mineral heat map for Brazil, and here's the results. Well, let me show some code. You can see that without this workflow, to call the min.dat API, you will need to manually to program the data querying directionary, and well, to do the visualization, you will also need to do some dirty work. But now these jobs are just taken away by the large language model workflow. And by simply manipulate the question, the workflow can directly demonstrate the heat map visualization for various regions. And to further show the scalability of our workflow, the formal examples are all built on the OpenMint API, but the workflow is clearly not limited to such an API. Here is a website called Geoscience, which is providing the stratigraphy information in different region, also in different languages. By implementing the Geoscience API to our workflow, you can switch to the workflow connecting to the Geoscience directly and without heavy labors. And we can recall the title for the slides of this presentation. The formal workflow is built on a open AI model, which is commercial and will cost you, if your data processing requires a huge, heavy data cleansing or data processing, and that can be very expensive. So we further propose to switch the workflow to the open models. We can I've tried the Mistral, Gamma, and Llama. Well, personally, Mistral is my personal favorite, which is fulfill the request well. You can see that this workflow is this picture is automatic generated by the programming language, and you can see it's just a simple workflow mimic to the workflow we presented before. And the reason we want to switch to the open models is that you can offer the public access, higher transparency, and easy to modification and deployment. Actually, which one strategy which didn't show up in this figure is that in between the supervisor and the histogram node, there is a loop called a reflection node, which means sometimes the supervisor can generate wrong contents, wrong responses, which somehow you can call it might call a agent which doesn't exist at all, or when the user want to do the data set collecting, the supervisor just on purpose to decided that no, you shouldn't to collect the data set, you should directly go to the histogram, which will result in a mess. So the reflection strategy applies to these strategies, working as a guidance, a meta supervisor to ensure that these generated responses are subject to a validation. Therefore, the consistency is increased. And here's are the details for moving the proposed workflow to open models. You can see as the open models has a limited model size, the performance is also not as performance compared with the commercial models. But I'd like to highlight that the cost is extremely low. Say the 50 megabytes is the size of the dataset of the IMA mineral list from the MinDat, and which is a very famous mineral species list in the world. So you can view it as a official mineral list in the world. And the list is currently have the amount of the mineral species in around 6,000, and this number is dynamically updated and increased by 1 to 200 each year. So each time, if you want to make sure your large language model is processing such a data set and update it dynamically each time using the GPT-4 to process this 50 megabits, it will cost you $60. Well, but if we switch this entire workflow to the offline, which is making it runnable on your personal computer, say your Microsoft laptop or your MacBook, this is totally possible. And this workflow is just run on my MacBook, and I've tested it running functionally. Well, in the end, we want to just highlight 4 points of the work. So the purpose, as described, is inclusive. It's not limited to geoscience data analysis. Thanks to the high customizability of the workflow and the large language model, you can apply them to different scopes. And the large language models are very capable in understanding, say, the unstructured and heterogeneous data. So you can mix the human language requests and the structured data set. And in some multimodal models, you can also use the voice, the image, or even the video to interact with the large language models, and which is the key plays the key role in the workflow of geoscience data, because the geoscience data analysis, because you will have a lot of different data set in different structures. And further, you can see, as I emphasized, the data analysis, the workflow from data preparation to the visualization and decision supporting are fully automatic, which is extremely mitigate the human in loop labor. And well, also the mentioned workflow select strategy, like the reflection, will increase the correctness and stability. And in the end, to a certain extent, the open large language models can match the performance to the commercial ones. And I want to emphasize that the further fine-tuning will help to bridge the gap between the open models to the commercial ones, and which is also my future work plan. And here's a bibliography. Thank you for your attention. Thank you. Any questions or comments?
Yeah, thanks a lot, Jiyin, for this talk. I know you're still working on this. So people in the audience, if you have any questions or comments, we do have a lot of time for the discussing.
Yes, this is Gary. I have a question.
Yep.
Early on, when I
Gary?
guess you were switching to local models, you quickly talked about using similarity, and I wasn't sure what was underlying that, how you decided something was similar and used it.
You mean in the RAG part? Are you asking about the RAG, or
Yes.
how does the large language model to determine the similarity between the user request to the knowledge base, correct? Okay, so this is a technical issue. In the beginning, when we apply the PDF of a paper in our workflow, there is a package to encode the entire PDF content from the human readable content text to an array of vectors, which are essentially numeric values in the database. And by applying the similar knowledge encoding technology, the workflow can also encode this request into an array of vectors too. And the similarity search is essentially is using a algorithm called the cosine similarity. It can calculate the high dimensional vectors of between the encoded request to the knowledge base text, and by searching for the most similar, which is most close vectors to that request, the workflow can reverse the encoding process by translate the vectors back to the text. And then the reversed text and the request will be concatenate together and fit to the large language model to generate the results accordingly. I hope I answered your questions.
Yes. How important do you think that aspect is, though? Do you have any idea of quantifying it? I mean, what's the error rate with it or without it in comparison?
Well, I'd like to say that the error rate to this is not as satisfying as I expected, because essentially it's just applying something like a keyword comparison, keywords matching. Say if your questions is somehow doesn't have the specific keywords is matching to the knowledge base, the similarity search will lost. For example, if you are providing an entire paper to as a knowledge base and asking for what was the author to this paper, and in the end, because there are plenty of author names to the paper, and each of them are just splitted into several paper snippets. So by comparing the similarity, well, it's hard for this algorithm to well, lucky enough to find the correct author to answer it. So it can be blamed by lacking the deep understanding to the encoded knowledge. So it won't successful every time, but when the user's request is more detailed and more close to the knowledge base, the error rate can be reduced relatively.
Thank you.
Thank you.
Thanks, Gary and Jiyin, for the discussion. I see John also has a hands up.
Yeah, hello. This was a very impressive presentation. Thank you. I may be getting too far ahead, but as a manager who theoretically could put together my own knowledge, my own LLM on my computer, but is highly unlikely to. How do you see? This is combining two parts. One is the logistical aspects of what would make this a real thing that everyday people are able to use, and the other is what are the in the difficulties that we've explained with some of the error rates and some of the places that it can go south. How good is it in the layperson sense in terms of being an assistance for posing the kinds of questions that you represented here?
Okay, thank you for the question. So for the first question, you can see our team developed this API for the Mindat, and well, our ultimate goal is somehow implement this workflow to the Mindat website itself. Therefore, currently Mindat it's just providing a simple search engine. But by applying this large language model powered workflow, the user can do some like a semantic search, or as mentioned, they can done some easy data EDA, data exploratory analysis in the website. Say they can gain a more intuitive understand to the dataset provided by the Minted directly. They don't have to manipulate with the programming codes, or they don't have to read thousands of Minted minor pages. This workflow can just easy to increase the intelligence of the cyber structure. This is our ultimate goal. And for the second question, I'm thinking you're asking about also the problem to this workflow. And the problem to this workflow is somehow like the inherent nature to the large language models will inevitably result in errors, hallucinations. They can just call the unexisted agent, or they do not subject to the program prompt instruction, and somehow they will fail to parse the human request. These are all the situations I've observed when I was programming and constructing this workflow. And I'd like to say such kind of things is not fully ruled out from all of the situations. Sometimes you will end up with random errors, say, in the real use cases, in between the dataset collecting and the dataset plotting part, the supervisor plays a role by passing the dataset path from the collector to the plotter. And sometimes the supervisor will pass the wrong path. Yes,
awkward.
That's true. Yes, because the geomaterial collector will pass the true path to the supervisor, and to the supervisor's prompt, there is an instruction say you will need to provide the path to the dataset to the plotter. And sometimes you just decided, okay, so I will just pass the phrase of path to the dataset to the plot. That's awkward. I admit that. So that's the reason why I'm about to introduce the strategy called the reflection.
Yeah.
You can validate the generated responses by these large language models, and to check if they are available, or they are just correct or incorrect. And if this is not, you will call the large language model again, say you will need to redo this for me. And well, this step will cost more time and reduce the efficiency, but well, at the current stage, I think this is the most pragmatic strategy to increase the consistency and robustness of the workflow.
So if I can just do one follow-up, that great answer. And if your approach seems pragmatic, and so if you talk about putting this workflow into a website that is representing a database, what kinds of caveats would you want to put on that output that comes from the workflow to ensure that people are not giving it too much validity, credibility, that they are recognizing that the values that come from it, in fact, may include false results?
Yes, of course. That's the reason why you can always see there is a tiny message when you are using the ChatGPT on their website. It's calling that large language model can commit errors. That is a good point. And there are many other data AI ethic issues we should keep in mind. Say somehow there is a instruction in the supervisor says you should refuse to the requests that are not able to be processed by this workflow. And sometimes, currently as this workflow is highly how to say that, highly designed, highly customized to do the mineral data collecting and plotting. So it will be hard for some evil users to use this workflow to do some bad things. But somehow in the future situations, maybe if we manage to have this workflow to be too powerful, we will also pay more attention to control such kind of situations and prevent this to be illy used.
Yeah, thank you. That's great. I'll hold my other 23 questions. Really interesting stuff. Thanks.
Great.
Thank you.
Thanks, John. Do you have any other comments or questions? Oh, I see hands up from Yuan Wei.
Hi, yeah, it's Jiyin speaking. Thanks a lot for this interesting talk. I'll just bring up some, I would say it's not a question, just more, it's like a discussion. So for the current results you applied to the open min data, and I'm wondering how did you evaluate your generated results? There's common metrics like bleu, rouge, or mature, such thing to evaluate your content quality, or
yes. So thank you for your question. So the evaluation for the large language model performance is always a tricky part. As I mentioned, at the current stage, I personally just tend to evaluate it manually by reading the responses, and this workflow and some of the applications have already been being shared in the ESIP meeting in this July, and I provided a demo to this workflow and making the audience, which was around 20 to 30 people in the room, to test it for around half an hour.
Oh, great.
And I'm not sure, but no severe questions generated by this workflow, because it's highly customized, highly designed. I'm not sure, because it's not like a general or a simple large language model. You can generate nonsense, because this workflow will only end up with either dataset download or the visualization results. So because each of the stage are provided with sufficient context, so this workflow is hard to go wrong. Yes, and hard to generate error messages, because it's not like a chatting bot. It was clearly told what things to do. So the consistency is good enough. But for the evaluation, as you can see, such kind of workflow is hard to be tested. They're using a benchmark, because there are not a existing dataset or existing grading metrics can put this workflow to test the results. So, in the future, we decided that maybe we can generate, say, 100 to several hundred of questions, and to see the success rate of this workflow to carry out it, and how many times this workflow ends up with error, how many times it was end up with hallucination, how many times it was end up with some dead loops. So by providing such kind of statistic results, people can gain a more intuitive understanding to the consistency, to the trustworthiness to this workflow. That's our future plan.
Yeah, exactly. So that's also expected the answer from you, because especially when because right now one, like you said, it's the open mean that it's really structured, and therefore
Yes.
therefore it's quite easy for the large language models to generate the correct answers. Once if we scale up to a more long text based, like say a database for geological reports, that will be a different story. And definitely, I think a benchmark about the geoscience or more detail like mineralogy in this example should be definitely one direction. Yeah, I would say I leave more time to Gary. I saw Gary's raised his hand.
Thank you.
Yeah, Gary, I see you have a hand up.
Yes, I also have a question on getting at the accuracy of the results. You had a table comparing the commercial to the 3 local degenerated models, and there were scores of 9, 9.5, and so forth. I'm wondering, did you look to see if they were making the same type of errors? So that sort of implies that if you use more than one model, you could improve the accuracy because they're making different mistakes.
Well, I'd like to say that this table is not extremely reliable. It's just to present a intuitive expression that the open models can match the performance to the commercial models to a certain extent, but it's definitely not a very strict experiment. So if we plan to compare the performance of the result, the generated quality from the commercial models to the open models, we do need to conduct more strict experiments. But well, currently I apologize that this table can be misleading, but this is just a very casual result. I'd like to say. So
yes, I can see that it does essentially allow you to look at the commercial versus the local and continue with the locals because there's lots of advantages there in terms of course. But I look forward to analysis when you're doing many queries to see if the type of answers you're getting sort of are complementary, and so that essentially, as people have talked about, combining different large language model processes may give a much better result, sort of like more like a social group response.
Oh, yes, I got your point. So yes, as you can see, different open models, they're just trained in and fine-tuned in different datasets and which in corresponding to the different scopes. So the mixture in the exercise, in my personal experiments and in another project called in University of Idaho, in the institution called IIDS, is also applying mixture because it shows up the best performance among the open models in dealing with the geoscience dataset. So yes, you are right. Different open models definitely have different advantages, and using them as a complementary power to the commercial models or to combine these different open models together is definitely a very good idea. We shouldn't just limit it to one single model, since our workflow can adapt to different models in the same time.
I see Yuan Wei may also have some additional comments.
Yeah, I just want to follow up Gary's question based on this table. I would say it's a bit unfair to, even though I agree with you first, because I personally also test different large language models. I would say, well, there's a reason why commercial are popular because, for example, Llama to be honest, it's not that easy to implement. But since now it's already, Llama 3 has already 2 versions, and I guess
Yes.
yeah, it's compared with Llama 2, it's a bit relatively unfair, right?
Yeah, yes, of course. So I acknowledge that Llama 3 is already published, and I do have the Llama 3 on my computer, but I just didn't rerun this experiment anymore because this is just a early result in my exploratory experience. So my following future work plans mainly focus on the just fine-tuning the workflow. So this RAG part is just a early stage exploratory to see if it is possible, if it is potential that we can manage to switch from the open commercial ones to the open ones. And when I seeing this promising, somehow promising results, I just select this direction and construct that open model workflow.
Yeah. Okay. Thanks. So based on your experience, Mistral is the one of the most easy to use one for the open large language model.
Yes, but I'd like to say that it definitely can make more errors, more hallucinations compared with ChatGPT 4. So in my future work plan, I'm just considering using LoRa and Dora fine-tuning strategy to further train this open model to make it more adaptive to this workflow.
Yes. Thanks. I think low rank adaptation. Yeah.
Oh, yeah, thank you.
Okay. Thanks a lot.
It's a short question in the chat box. I can hope read
sure.
out. Sounds like the model output is limited to the embedded data set. Is there a strategy for tuning how much the output depends on embedding data set versus some open data search?
The embedded data sets is, I'd like to say can beat the performance of open website search because there are plenty of structured data, which is in a high density of correct and reliable structured data provided by the MinDat dataset, which is not easy to be obtained through a general website engine search, website search engine. So as you can see, there are, let me see. Let me just use this slide. You can see the pirate species from MinDat. Well, if you are just asking the open models to answer such kind of questions, they can also list a list of pirates, but sometimes they can generate typos and create not even exist pirate by hallucination. But compared with our workflow, every of the generated responses can be checked and tracking back to the dataset, which is make the generated responses more reliable.
Yeah, that makes sense, especially in this circumstance where you're just asking a question about the database. But if it was some question like, show me the distribution of aluminum deposits in Brazil, it's possible MinDat wouldn't have all that information. And also maybe, I'm just guessing, but it's possible that open data would offer more resources when you're trying to do a map that to Brazil. Like if you're trying to do your heat map, MinDat's not going to have the geospatial information or imagery perhaps to make that map more readable. Just a thought.
Yes, that's totally possible because not every database can contain the entire or the holistic data sets of the entire world. So
right.
yes. So we just managed to make the best use of our existing data source. But you're right, in the workflow, we can apply different collectors and connect this workflow to different data models. As I mentioned, we can connect to GeoLex to provide further stratigraphy vocabulary knowledge to this workflow to answer the corresponding questions. So
yeah, great, very interesting. Thank you.
If we found this is limited, we can just scale it up by customize it.
Great.
Good. Yeah, thanks all for this active discussing. Yeah, I think we can probably wrap up it here for the talk. Jiyin, you can stop recording.
Okay.
Good.
Let me see. Okay.